Okay, great. Good morning, everyone, and welcome to Lecture 19 of 124103, Biophysical Principles. This will be the start of another topic that we will learn in this course. If you'd like to think of the topics as modules, then this would be the last module in this course, where we'll talk about waves, including sound waves. But to begin the discussion on waves, we will first talk about periodic motion. So in this lecture, we'll talk about periodic motion. And from these concepts of periodic motion, we'll be able to talk about waves in the next lecture. And then next week, for the last two lectures in this course, we will be talking about sound waves as a particular example of waves. Yeah, so 4 more lectures left in this course, and those 4 lectures will be devoted to the topic of periodic motion and waves. All right. So in this lecture, as I've mentioned earlier, we'll talk first about the basics that we need to understand waves. We will talk about what periodic motion is. It's sort of not a very new concept, because you've already encountered periodic motion in lab 4 and in the most recent lab that you've done. But we will still define the parameters of a periodic motion, and we'll talk about a specific kind of periodic motion called simple harmonic motion that is characterized by a sinusoidal graph. And we'll talk about what a sinusoidal graph is, and then we will identify the parameters that describe the periodic motion and the sinusoidal graphs, in particular the amplitude, frequency, and the period of the simple harmonic motion or the periodic motion. And when we're talking about periodic motion, especially about frequency, we can relate that to the motion of an object around a circle. And so it will be so we will also talk about the angles that the angle in reference to the circular motion of the object. We'll talk about degrees and radians. So the angle can be measured in terms of degrees and radians. And in this lecture, we will distinguish between the two. We will differentiate and convert the angles between degrees and radians and vice versa. All right, cool. Okay, so let's start our discussion periodic motion by looking at what it is. So as I've mentioned earlier, you've already encountered periodic motion in lab 4. It's essentially a motion that's repetitive. So any motion that repeats itself, then that's cyclical, can be termed as a periodic motion or an oscillation. But we will focus on a particular specific kind of periodic motion called simple harmonic motion, or SHM. SHM, or simple harmonic motion, has certain characteristics to it for you to call a periodic motion simple harmonic. So here's a good example. I have a car. I don't know if you can see. Yeah, hopefully. Yeah, the car is connected to 2 springs on both ends, right? So of course it's in equilibrium initially, but if I pull the car on one end and let go of the car, notice how the car oscillates to and fro. Okay, the car is undergoing simple harmonic motion, for one, because it has a stable equilibrium position. It's that position there where it's not moving. And then if I displace the object, when I pull the car to one side and let go, the spring will try to bring the car back to its original equilibrium position. And so there's this force from the spring that tries to restore the car to its equilibrium position. And this is the most distinguishing feature of a simple harmonic motion is you have this force provided by the spring that will bring the car back to its, that attempts to bring the car back to its stable position. So similarly, if you have an object hanging by a spring, okay, and you let go of it, right, the object oscillates up and down because the spring will try to bring the object back to its original equilibrium position. Yeah. So those are examples of simple harmonic motions. And the last characteristic of SHM is that the graph of the motion is sinusoidal. So what do we mean by sinusoidal? Okay, so here is an animation of the object on a spring that's oscillating up and down. So this is the initial equilibrium position. If you pull the object downwards, the spring will try to bring the object back to its equilibrium position, but the object will overshoot that, will go up. And so you have this periodic up and down motion. If we trace the motion of that object, it will just be a straight line, right? If we trace, let me see my pen. Right, so if we trace the motion of that object, it will just be a straight vertical line because that object's just going up and down. But imagine if I, for example, connected a pen at the end of this oscillating object, and I moved the paper underneath the object, you'll imagine the object's going up and down, but the paper is moving. The paper where the pen is writing is moving. Then the up and down motion will trace sort of this pattern. This pattern that you also see up here. If you extend that to a longer time, then you'll see this up and down pattern here. And this pattern is what we call sinusoidal. Yeah, and because and that's why you'll see why a sinusoidal graph is a characteristic of simple harmonic motion, because the sinusoidal graph is traced out by the periodic up and down motion of this object about its equilibrium position. Okay, if you notice, this is the equilibrium position, and the sinusoidal graph is sort of symmetric about this equilibrium position. So if you also define the equilibrium position there. All right. Okay, so then knowing what a simple harmonic motion is and what a sinusoidal graph is, we can then define some parameters that describe simple harmonic motion. So here's the sinusoidal graph that we've seen earlier. So the middle point, this is the x is equal to 0 position, the equilibrium position where x is equal to 0 or displacement is equal to 0. And notice how the object oscillates about this equilibrium position. So we can define what we call the amplitude, which is the maximum displacement from the equilibrium position. Okay. It's usually how far you pull the object away from the equilibrium position. So for this car, if I pull it, say I pull it about 2 centimeters to the right, the car will oscillate about that 2 centimeter mark, meaning the maximum oscillation, the maximum distance that the car will reach as it oscillates will be that 2 centimeter mark, which is the initial displacement of the car from the equilibrium position. Okay, so that's the amplitude. Okay, the sinusoidal graph is symmetrical about the equilibrium position. So you can measure the amplitude whether going upwards to the peak or downwards with respect to the equilibrium position. It should give you the same measurement for the amplitude. And because amplitude is displacement, the unit should be in meters. Okay, period, you've seen this in lab 4 where you use the pendulum and you measured the time it takes for one oscillation. So that's what we call period. It's the time it takes for the object to complete one cycle of its motion. So that's so for example, this is the object and it starts from, for example, from the stretched position. If it goes up and then goes back down to its original position, that's one period. Okay, so one cycle. So in the graph, in the sinusoidal graph, it's the distance between two successive points. So you can measure between two peaks, for example, but it doesn't have to be the peaks that you measure. So you can also take this point and the next successive point just before the pattern repeats itself. And this is also one period in the sinusoidal graph. So two successive points just before the pattern repeats. That's how you identify the period from the sinusoidal graph. Okay. And frequency is the number of cycles per unit time. It's defined as the inverse of a period. So frequency F, okay, we use the symbol small f, it's just the normal small f. It's the inverse of the period that gives the frequency. It's the number of oscillations per second. Okay, and it's measured per second or number of cycles per second, and it has a special term called the hertz. So frequency is hertz, but period, because period is time, it's measured in seconds. Okay, so period seconds, frequency hertz. Or yeah. Okay. Right. So those are the three parameters that describe simple harmonic motion. There's a fourth parameter called angular frequency. And to understand angular frequency, let's relate the motion of the oscillating object to its motion around a circle. So if you think about, so here's the animation on the right, you have the object that's just bobbing up and down about the equilibrium position. You can also think about this up and down motion as the object rotating around a circle, right, periodically. So one up and down motion is equivalent to the object going around a circle. So if you think about it, if you have an object that's going around and around a circle, it's also periodic motion, right? Periodic motion is anything that repeats itself. And so you have this object, for example, starting at that point and going around that circle, then that's one period. And so we can relate the motion of this object around the circle as equivalent to the motion of this object on the right that's going up and down. Okay, so one vertical oscillation can be thought of one round around a unit circle. So a unit circle is a circle whose radius is equal to 1. Yeah, so we set the radius equal to 1 just for simplicity, so we don't have to worry about how big the circle is. So if we do that, if we relate one vertical oscillation to the motion of the object around a circle, then we can say that in one oscillation, the object would have covered a distance that's equal to the circumference of the circle, right? Yeah, so notice here in the animation, right, one up and down oscillation is equivalent to the object going around the circle. Okay. And the distance around the circle is the circumference So the circumference is the distance around the unit circle. Okay, and for a circle, the circumference is defined as 2 pi times the radius of the circle. So this is a basic mathematical definition for finding the circumference of a circle, 2 pi times the radius of the circle. But for a unit circle where radius is equal to 1, the circumference is equal to 2 pi. So that means that in one oscillation, in one up and down motion, and therefore in one round around the circle, the distance that's covered by the object is equal to the circumference, which is equal to 2 pi. All right. Okay, so the up and down motion, we've seen that the up and down motion is also translated as a sinusoidal graph with a period t. And essentially period is the time it takes for one up and down motion. And so period is also the time it takes for one round around the unit circle. So we can then define the speed for which the object oscillates and the speed for which the object goes around the unit circle. From the basic definition of speed, speed is distance over time. What do you think is the distance? So we're talking about the speed of this object that's going around this unit circle, which is also the speed of oscillation of the object. So what do you think is the distance covered by the speed by this object that's going around the circle? Yeah, good. The period. So the period, that's the time it takes for one oscillation. So the period will go into time, period having the units of seconds. Okay. And the distance that's traveled by the objects will be the circumference of the circle, right? Because the object goes around this circle, so it would have traveled the whole length of this circle. And the length of this circle is the circumference, which we've seen earlier to be equal to 2 pi times the radius. But for a unit circle, radius is equal to 1. So you have the circumference is equal to 2 pi. And as Willow said, the time will be the period. The time for one oscillation will be the period. Okay, so in one period, in one up and down motion, or in one period of the sinusoidal graph, okay, the object has gone one round around the circle, and the distance around the circle is the circumference of the circle. So then we can write speed to be equal to 2 pi, which is the circumference of the circle, which is the distance traveled by the object, divided by the period. So the speed of oscillation of the object will be equal to 2 pi divided by the period. And this speed has a special name. It's called the angular frequency. Right, so angular frequency is essentially just the speed for which the object goes around the circle, and it's equal to 2 pi divided by the period. But what the angular frequency does is it allows us to relate the sinusoidal motion to the movement of the object around a unit circle. Okay. The angular frequency equation is given here. It's just the speed around the unit circle, but it has a special name, angular frequency omega. It's the Greek symbol. Okay, right? It's a fancy W. Okay, a fancy W called omega. So angular frequency omega is equal to 2 pi divided by the period. The unit for that is radians. So the distance around the circle is measured in radians. And of course, period is the time it takes to cover that distance. So it's in seconds. So the unit for angular frequency is radians per second. Okay, in terms of the frequency, because we know frequency is just the inverse of the period, we can then write the angular frequency in terms of the normal frequency f. Angular frequency is equal to 2 pi f. So just be careful here. There are now two kinds of frequencies. So omega, that's the angular frequency. And you have f, which is just the normal frequency, which we just simply call frequency. So if you if we say frequency, then that refers to just the f, the normal frequency, which is the inverse of the period, how many oscillations there are in 1 second. That's the normal frequency. But if there is angular frequency, you can think of that as the speed for which the object rotates around a unit circle. And that's 2 pi, which is the circumference of the unit circle times the frequency, or 2 pi divided by the period. Okay. And the unit for angular frequency, again, is radians per second. Right? Okay, so radians, let's talk a little bit more about the radians. Okay, what is radians? Radians is essentially just the distance around the unit circle, right? So that 2 pi is the whole distance around the circle, which is the circumference of the circle. And radians is also a form of an angle. But radians is essentially the distance around the unit circle, and the distance around the unit circle is what we call arc length. Okay? So that one round around the unit circle, that's the circumference of the circle, that is 2 pi. So let's just look at so 2 pi, we've already encountered that. That refers to 1 round unit circle, essentially going from this point and back to that point. That's 1 round. So that's an arc length, or a distance of 2 pi, which is the circumference of the unit circle. If you just go halfway, starting, so let's put this as the origin. Get rid of this. So if that's the origin or reference point, how do you get rid of this? Yeah. If you just go halfway around the circle, if you just go halfway around the unit circle, so that will be half of 2 pi. And so that's why halfway will be pi radians, an arc length of pi radians. Okay. Right? So one round around the unit circle has an arc length of 2 pi, okay, the circumference of the unit circle. Half round, just halfway, will have an arc length equal to half of 2 pi, which is just pi. Right? And right, quarter of the way. So if you just go quarter of the way around the unit circle, then that will be 2 pi divided by 4, which is essentially just pi over 2. And 3/4 of a way, you have 2 pi divided by 3. 2 pi over Yeah, right. So quarter of the way here. And this one's like 1 pi over 6. This is just like if you divide half of the circle into 6 parts, 1, 2, 3, 4, 5, 6, then going from this origin to one part of that division will just be pi over 6, because one half cycle will be pi. And if you divide, if you're going 0 to pi and divide that into 6 equal parts, then one part will be pi over 6, 2 pi over 6, 3 pi over 6, and so forth. But the special angles that we will encounter a lot will just be 2 pi, and maybe pi over 2, and pi. So these are the 3 special angles that I would say you will be encountering quite a lot. 2 pi being one round around the unit circle, so that's the circumference. Pi over 2 is just halfway. I'm sorry, pi over 2 is quarter of the way, and pi is halfway around the unit circle. Right. So the distance is measured in terms of pi in radians, but we can also measure the distance in terms of angles in degrees. And so here you can also see angles. 0 degrees is the reference point, but when you go around the circle, 0 degrees is also equal to 360 degrees. Right. So from that relationship, you can see 2 pi is equal to 360 degrees. That's one round around the circle is 360 degrees, right? And then halfway pi will also be equivalent to 180 degrees, right? And pi over 2, quarter of the way, is equivalent to 90 degrees. 90 degrees, okay. Right? Okay, so I guess the key takeaway point from this slide is that, you know, the motion of the object around the unit circle, by looking at the motion of the object around the unit circle, you can measure the distance traveled by the oscillating object around the unit circle, and the distance is related to the arc length measured in radians. If the object went around the unit circle completing one full cycle, then the distance traveled will be 2 pi radians. And 2 pi radians is equal to 360 degrees. If the object went halfway, that will be pi radians, which is equivalent to 180 degrees. Quarter of the way, it's pi over 2, or that's equivalent to 90 degrees. Okay? And here we can see then that the distance that's traveled as measured in radians is equivalent to the angle around the circle relative to this 0 degree position. So the 0 degree position is this horizontal axis pointing to the right. So 30 degrees is measured, for example, as such. 180 degrees is measured relative to this positive x-axis, if you'd like to think of it that way. Okay. But angles are easier to measure rather than radians. Okay. So we can, for example, the object, at some point the object is here. It's easier to measure the angle of this line relative to this 0 degree angle. It's easier to measure that angle rather than measuring the arc length in terms of radians. And so we should be able to convert between angle in degrees to the radians, which is the distance around the unit circle, for us to find the angular frequency. Okay. For the special radians like 2 pi, pi over 2, and pi, conversion between the radians and angle is relatively straightforward. But for different angles, converting between degrees and radians would require us to know some conversion factor, right? So it's still the same technique whenever you're converting between angles and radians, degrees and radians, you'd still need some conversion factor. And the conversion factor will be this pi and 180. Okay. It's essentially this relationship, because pi radians is equal to 180 degrees. Of course, you can also use this relationship, 2 pi is equal to 360 degrees. You can also use that as a conversion factor, or pi over 2 is equal to 90 degrees. You can also use that as a conversion factor. Yeah, pi equals 180 degrees is just more straightforward because you don't have this factor of 2 that's being multiplied or divided by pi. So we'll use that conversion factor. Pi is equal to 180 degrees to convert. So when you're converting from degrees to radians, you multiply the degrees with pi over 180. And when you're converting from radians to degrees, you multiply the radians with 180 divided by pi. Right, so say 30 degrees. How do we convert 30 degrees to radians? We simply multiply 30 degrees with pi divided by 180. Right, so that pi in your calculator, I don't know if you can see, that's right, so in your scientific calculator, or this doesn't even have pi. It's that one that you have EXP. So it's 3.1416 is what you use for pi. So you should have 0.52 radians for 30 degrees. Okay. 3.1416 something divided by 180 times 30 should give you 0.52 radians. Okay. Yeah, good. Yeah, that's right, Vilo. And then how do we convert pi over 4? Okay, so pi over 4 radians. Whenever you see there's a symbol pi, the unit of that is radians. So pi over 4 radians, how much is that in degrees? Okay, what you have to do is to multiply pi over 4 with 180 divided by pi. So you have pi over 4, you need to multiply that with 180 divided by pi. Right, pi will of course cancel each other out because anything divided by itself is equal to 1. So that's equivalent to just doing 180 divided by 4. You should get 45 degrees. Good. Right. So I guess this will be very useful conversion factors that I would encourage you to put in your formula sheet that you're building for the exam. Yeah, converting degrees to radians, multiply with pi over 180, radians to degrees, multiply with 180 over pi. Right, so just try this exercise here. Convert 60 degrees and 135 degrees to radians, and then try to convert 2 pi over 3 and pi to degrees. Okay, so 60 degrees. Okay. When you're going from degrees to radians, you have to multiply with pi over 180. Okay. Right, so you should get 1.05 radians for 60 degrees. So you can do pi divided by 180 and then times 60, or you can go 60 times pi divided by 180. Any scientific calculator should be able to do the bed mass correctly, even without using brackets. Yeah, and 135 degrees, the same procedure, multiply with pi over 180, you should get 2.36 radians. Cool. Right, and converting 2 pi over 3, you have to multiply with 180 divided by pi. So you go 2 times pi divided by 3 times 180 divided by pi, 120 degrees. If you're having trouble getting 120 degrees, try to put brackets in your calculator like this. Okay. Otherwise, if you just put 2 pi divided by 3 times 180 divided by pi, what your calculator will do is it will divide 2 pi with 3, multiply that with 180, and then divide it with pi. I mean, yeah, sometimes it depends on different calculators, needs different bracketing and stuff, but yeah. But if you cannot get 120 degrees, check your brackets. Maybe your calculator needs brackets. Okay, for pi, we don't even have to do this whole conversion. It's the conversion factor. We know pi is equal to 180 degrees. Okay. Right. Any questions so far? Are we happy with converting radians to degrees and degrees to radians? Good. All right. Good. Okay. So that was just a little bit of a segue, converting radians to degrees and degrees to radians. Let's go back to the periodic motion and simple harmonic motion. Yeah, so we've seen if you have an object that's oscillating up and down, then you can, so that's essentially the equilibrium position there. So for example, you have this object on a spring that's at equilibrium position. If it oscillates up and down, so this point in the graph here, that's when your object is at its maximum displacement over there. And up here, that point in the graph there, that's when your object is, I should have the same measurement. So up there, that's when your object is sort of compressed about that. Yeah. Right. So the oscillation, the up and down oscillation or to and fro oscillation of the object about the equilibrium position is described by the sinusoidal graph. And from the sinusoidal graph, we can pick out the period of oscillation. That's the time it takes for the object to accomplish one cycle of its motion. And that's the time between two successive points in the graph. So pick up 2 points in the sinusoidal graph just before the graph repeats itself. That's the period. And then the amplitude, that's the maximum displacement of the object. Okay, so this is also the amplitude here. Okay. Right. And then these two, the amplitude and the period, that's what you can read or pick up from the graph, from the sinusoidal graph. Once you know the period, you can then calculate the frequency f, the normal frequency f, by getting the inverse of the period. So f is 1 divided by the period. And once you know the normal frequency f, or once you know the period, you can then find the angular frequency omega. That's equal to 2 pi times the normal frequency, or omega is equal to 2 pi divided by the period. Okay. And by knowing these 4 parameters, we are able to completely describe the simple harmonic motion of the oscillating object. Okay, the 2 critical points, the amplitude and period. I think the critical point is for you to be able to determine the amplitude and the period from the sinusoidal graph, because especially the period, once you're able to determine the period from the sinusoidal graph, then you will be able to determine the frequency, and then you will also be able to determine the angular frequency of the object. Angular frequency is, of course, just the speed of the object's rotation around a unit circle. Yeah, and angular frequency is measured in radians per second. Cool. Right, so we can then, so this is the graphical representation of the simple harmonic motion, but we can also describe this graph using a mathematical equation. And the mathematical equation for simple harmonic motion is a sine and cosine function. So notice how it has this similar form. So x is equal to a sine omega times t, and x is equal to a cosine omega times t. So there are two possible cases for the mathematical equation that describes the simple harmonic motion. For the first case, where you have a sine function, this is when the object starts from zero displacement, from the equilibrium position. Okay? And we'll look more into the graphical representation of that in the next slide. But for the cosine function, if you use a cosine equation to describe the harmonic motion, simple harmonic motion, that's when the object starts from the maximum displacement. Okay. But let's just define what the variables are in this equation. So x, that refers to the displacement of the object, okay, where the object is during its oscillation. A, that's the amplitude, we've seen that already, and omega times time is the frequency. So t here is just the normal time, time in seconds. Okay. And omega is, of course, the angular frequency in radians per second. Okay. Right. And we call the angular frequency times time, we call that as the phase of the oscillation. Okay. So amplitude, we've seen that as the maximum displacement, and it's always the same regardless of where the object starts from. So regardless of whether the object starts from zero displacement or from the maximum displacement, the amplitude A will still be the same. It's how far, right? So in my illustration here, it's how far you initially displace your object from the original position. That's the amplitude. The displacement, on the other hand, changes because it's where the object is located at a certain time t. Okay. So often you want to find, so this equation gives you a way of finding where the object is located at a particular time t. Okay. Right. And similarly for the cosine function, they all mean the same. X is the displacement, A is the amplitude. omega's angular frequency and t is the time. So really the only difference between these two equations is whether the object started from the zero displacement, from equilibrium, or from maximum displacement. All right, so let's look at the graphs for these two equations. Okay, so in this first graph, right? Yeah, so this is the equilibrium, so x is equal to 0. That's the equilibrium position for the object, right? So for the first graph, notice how the sinusoidal graph starts from the x is equal to 0 point, meaning the object started from the equilibrium, from its equilibrium position, and it oscillates up and down about that equilibrium position. So if you see such graph that starts from x is equal to 0, x is of course the displacement of the object, then the mathematical equation that you use to describe this sinusoidal graph should be this a times sine of omega times t. Okay. Right. And right, for the second graph here, x is equal to 0, the equilibrium position is, of course, is always at this point. But notice how the sinusoidal graph started from this point, okay, from the amplitude. Okay, so if this is the amplitude, you notice how your object started from x is equal to a is the amplitude A. So notice how the objects started from its maximum displacement, the amplitude, and then it oscillates about the equilibrium position. For such graph, the mathematical equation that describes it is amplitude times cosine of omega times t. Right. Okay. All right. Yeah, the biggest confusion I usually find students making from historically is not knowing, which equation to use. Okay, but which equation to use really depends on where the object started oscillating from. If it started oscillating from the equilibrium position, and you will know that usually either from the graph, okay, or from the worded problem, which says the object started from equilibrium position, then the equation for finding the displacement of the object at any time t should be this sine function equation. Okay, if the problem says the object started from the maximum displacement, or says the object was displaced 2 meters from the equilibrium position and then it started oscillating, then that will be this graph here where the object started from the maximum displacement. So when you were wanting to find where the object is at a certain time t, then you use the cosine equation. Okay. Right. So say an example is, for example, you wanted to find, for example, a time. So this is 1 period. So this is half a period. Say, for example, at this time, at this particular time t, you wanted to find where the object is located at this particular time t in this graph. That particular time t is here. Okay. So at this particular time t, the object is at this point in its oscillation. If you project that to the y-axis, okay, that will give you the displacement of the object. And if you wanted to know what is the displacement of the object at this particular time t, then you have to use this equation, plug in the amplitude, and then you can find the angular frequency from the period, and then multiply that angular frequency with the particular time t. Right. It's probably easier to understand that by looking at an example, right? Putting numbers into these symbols. So let's look at an example. Okay. So here there's a 0.3 kilogram mass that vibrates according to this equation. It's just a formatting issue. So the x here, yeah. So x is equal to 0.38 sine 6.5 times t. Yeah, usually we don't put brackets like here, but yeah, it's implied that there's a bracket there. Sine of the whole thing, 6.5 times t, where x is in meters and t is in seconds, and we are asked to determine some other parameters. Okay. Right, so let's go through each of the questions here to see how we can use the given information to solve the problem. So the given information you have here, the vibration is described by this equation. X is equal to 0.38 sine 6.5 times t. If you compare that, what's the given equation to the form of the simple harmonic equation, we have two forms, right? For the simple harmonic equation, you have x is equal to a sine omega t and x is equal to a cosine omega t. But clearly, it's already given that it's the sine function. So if you compare the format for the simple harmonic equation and what's given, you can easily pick out the maximum displacement of the mass, right? So what's the maximum displacement of the oscillating mass? What do you think is the maximum displacement? Right? So recall, maximum displacement is also called amplitude. So the amplitude of the oscillating object will be the maximum displacement. Amplitude is this capital A, right? So if you compare the equation, you have x is equal to the amplitude. So amplitude should then be 0.38. Yep, good. Yeah. So it's really just comparing the equation for simple harmonic motion and what you're given. So any number that comes before the sine or the cosine function, that will give you the amplitude. Yep. So the amplitude or the maximum displacement is 0.38 meters. Okay. Right? Okay, and then so what is the angular frequency of the motion? So angular frequency is this omega. Yeah, good. So look at the equation, and any number that's multiplied to the time. So any number that's in front of t will be the angular frequency. Okay. So angular frequency is already the omega. So angular frequency will be 6.5 radians. Yeah, so I wasn't sure how you got 2.275 Willow. Yeah. The time t, I find this is often confusing students. So this is time, small t. Oh, okay. So 0.38 sine 6.5 times 1. If you do that calculation, then what you will find, what that gives you, what that calculation gives you will be x, the displacement when time is equal to 1 second. So in your calculation, 6.5 times 1, that means the time that you use here, time t, you used 1 second to be your time t. So the calculation that you did gave you the position of the object at 1 second. When 1 second after it oscillated, the position of that object is 2.275 meters. Because if you do the calculation on the right, if you do this calculation, what you get is x, and x is the displacement or the position of the object at a certain time t, which in your case was 1 second. For the angular frequency, it's the number that comes before time, because if you look at this equation, a sine omega t, omega is the angular frequency, and omega is any number that is in front of the time t. Okay, so you have 6.5 being multiplied to the time t. So it's just 6.5 that will be equal to angular frequency omega. Yeah. Does that make sense, Willow? Yeah, cool. So angular frequency is 6.5 radians per second. And then the next question is, what is then the frequency of the oscillation? So the normal frequency, right? So we know angular frequency is equal to 2 pi times the normal frequency. If we rearrange this equation, divide both sides with 2 pi to isolate frequency, then frequency is equal to angular frequency divided by 2 pi. So you have 6.5 divided by 2 times 3.14, which is 6.28, should give you 1.03 hertz. Okay. So 6.28, this is 2 pi. Okay, the period is just the inverse of the frequency. So 1 divided by 1.03. So I'll use the unrounded one, so we don't have rounding errors. So the period will be 0.97 seconds. Okay. Okay, what's the initial position of the mass at time t is equal to 0? What do you think is the initial position of the mass? Where did it start? Time t equals 0 means at the start of the oscillation. So there are only two possible answers here. Did the object start from equilibrium, or did the object start from the maximum displacement? Yeah. Good. It's at 0 because why do we know that it started? Yeah, very good. Yep, it started from equilibrium, and we know that because it's a sine function. Very good. Cool. Yep. Yeah. All right. Okay. So I think, yeah, the most crucial thing when you're given an equation like this is picking out the amplitude, which is just the number that's in front of the sign, and picking out the angular frequency, which is the number that is in front of t. So once you have these two, you can answer the period and then the frequency. And then draw a graph of x versus t showing the correct amplitude and period. Okay, we've already determined the amplitude and the period, and the initial position is 0. Therefore, your graph is always sinusoidal. Okay, but then your graph should start from x equals 0 from the equilibrium position. And your period is about 0.97 seconds. So notice how that's one period from this point. That's one period. So that should be around 0.97 seconds. And the position of the mass at time t equals 0.75 seconds. Okay, so this is now the calculation that Willow did earlier using this equation here, but this time the time is specified to be 0.75 seconds. Okay, so you have time t should be substituted with 0.75. Okay, and you carry out the calculation, right? You should get negative 0.38. If you don't get negative 0.38, check the settings of your calculator. It's really important that your calculator is set to radians. Okay. Yeah, and every calculator is different, so maybe you might want to check the manual of your calculator. Most calculators has a default of degrees for their angles. So maybe you need to go to the mode and yeah, I don't know, check the manual of your calculator, how to put your settings to radians. The reason why your calculator has to be in radians, right? Because this is omega, right? 6.5 omega. That's omega. Angular frequency is measured in radians per second. Right? Because the unit for omega is radians. When you calculate the sine, it should also be you should calculate the angle in radians. If you calculate it in degrees, you will get a different answer. You'll get a positive answer for one, and that will be incorrect. So make sure your calculator is set to radians, and you should get negative 0.38 meters. So what that means is that after 0.75 seconds, which is around here, right? So the x-axis is time, right? Time in seconds. So 0.75 seconds is around here. At this time, your object is located about around this point, okay? Which is, so that point there is around here. X is equal to negative 0.38 meters at that point. So that's where your object is located 0.75 seconds after it started oscillating. Okay. Right. Any questions about the solutions or the answers to these questions? Oh, yeah. Actually, that's, yeah. I think you're right. I also got, yeah. Let me just, yeah. Yeah, that's correct. Negative 0.37. The numbers are pretty straightforward because there are no rounding errors. 6.5 is given, 0.75 is given, and 0.3 is given. Yeah. Cool. Are we happy with the answers to these questions? How to interpret the equation and the graph? Good, right? Okay, that then ends our lecture for today on simple harmonic motion. Okay, knowing how to get the amplitude and the period from the graph is the crucial bit. Knowing how to pick out the amplitude and the angular frequency from the equation. We've also learned that and looked at an example of how to do that. Once you know two of the parameters, the amplitude and the period, you can find the frequency and angular frequency. And we also learned how to convert angles from radians to degrees and degrees to radians. Okay, so I'll keep that. The workshop is closely related to what we've learned.